In this example, we've got 4 different scenarios where we have the same equation each time. A is 1, B is minus k minus 4, and C is k minus 9. In the first one, if we got one root equal to 0, well, that's basically saying, hey, let alpha be equal to 0. So if alpha is equal to 0, we can substitute x being equal to 0, and the whole thing must be equal to 0, because that's what a 0 is. It's a root of an equation. So we sub 0 in, it just leaves us an equation with k in there, and this leaves us with k minus 9 is equal to 0, k must equal to 9. There's other ways to do that question, but that's probably the simplest. Same with b, there's probably more than one way to do this equation, and do this question, but again the simplest one is if we're told that a root is 3, then we just replace x with 3, because once we substitute a root being equal to 3 there, the whole equation must equal to 0. So we substitute the 3 in there, expand it out, collect like terms, as we've done there. We end up with a simple linear equation, which we're able to solve the 2k equal to 12, and k would equal 6 there. This time we're told the roots are reciprocals of one another, so we let one root be alpha, the other root be 1 on alpha, and that would be equal to the product of the roots equal to c on a. And c was k minus 9, a is 1, the reciprocals multiply to give us 1, k minus 9 over 1 gives us k minus 9, and k would have to be equal to 10. In D here, roots are the same in absolute value but opposite in sign, so one root's alpha, the other one would have to be negative alpha, and sum of the roots is equal to minus b on a. So the sum of the roots is 0 in this case. We simplify the negatives, just gives us k minus 4, and if k minus 4 is equal to 0, k would have to be equal to 4. Again, we're going back to trying the simplest way we can do these questions, and using product of the roots, sum of the roots, and the idea of what a root actually is to solve those equations.